great pleasure for me to introduce Professor Geert Leus today as guest presenter. Professor Geert Leus got his PhD from U11, and for many years he is now a professor at Delft. He has worked extensively in signal processing, and he is a distinguished lecturer of the IT Signal Processing Society. And today he is going to give a lecture, a meet in three lectures he gave in Greece, or will give it in Greece, entitled Graph Signal Processing, Filters and Spectral Estimation. I suspect that it's very interesting. So we will learn today about graph signal processing. So, looking forward to your presentation. So if you have any questions, please, at the end of the presentation, come up with a mic so we can have the sound.
Thank you, Thanasis, for the introduction. So it's a pleasure to be here. I've been in Crete a couple of times, but always as a tourist, so this is the first time I've come on official business. I understand it's also the last day of the semester, so thank you all for coming to this talk. So I will try to give an introduction, small introduction in graph signal processing, and then specifically also focus on filters and spectral estimation. And this is joint work with many students and postdocs from the TU Delft, but also external collaborators. And I would like to thank the IEEE Signal Processing Society also for sponsoring this lecture tour. Good, so what are we talking about here? So you're all used to working with signals that usually live on a regular grid. Think of audio signals, audio signals, video, images. So they either live in time or in space or in space-time. So we can say that these are very regular structured signals. Here in graph signal processing, we try to focus on signals that have a very irregular structure, and we try to capture that structure by means of a graph. And that's so where the name graph signals comes from. So we basically have a domain that is not time or space-time, but the domain now of the signals will be the graph itself. And this has many different applications, or let's say many different fields where we can think of such signals. Think, for instance, here of a sensor network where you have the different sensor nodes and they measure some temperature or pollution. And in that case, the nodes are the sensors, and what they measure is basically the graph signal. And we will construct edges between these sensors whenever these measurements are kind of similar in some way. It doesn't necessarily mean that these sensors are close to each other, but the measurement, the data is somehow similar on these two locations. Because you could have, let's say, two sensors that might be very close, but maybe they have different altitudes, or maybe there's a mountain range in between, so it doesn't necessarily mean that they have related measurements if they're close. So that's basically what the graph captures, data similarity. And you could construct such a graph maybe based on historical data or something like that. Another example is here this kind of a road network, where the graph, of course, is trivial there. It's just the road network itself. The nodes are the junctions. And a possible graph signal could then be, for instance, the number of cars that cross a junction, for instance. Another example here are brain networks. So in that case, the graph is kind of the anatomical brain graph, so how the different regions in the brain are connected to each other. And your graph signals on these nodes, in these areas of the brain, could be fMRI signals or EEG signals or something like that. So whenever we will process this data, it is much better to actually process them taking this graph into account than just process them in a spatial domain or in a temporal domain. Because this graph captures much better the data structure than the spatial domain. Also, the brain, closeness of two regions in the brain doesn't mean that they are connected, right? So we have to really take the true anatomical brain graph into account, right? So that's what we will be talking about here. So processing these signals, taking the graph into account. So the graph to us throughout this talk is kind of given from some other fields, right? It's either the road network, or it's the biomedical people that tell us, okay, this is the brain graph, or it's some scientists have measured this graph here based on historical data. So the graph is basically extra prior information that we will use in graph signal processing that you don't have in classical signal processing, and that's why we have the potential to do better than classical signal processing, because we take the true domain of the data into account. And in all these cases, you see that actually what is measured is basically a time series on every node, and that is true in most of these scenarios. So which means that we actually have two domains. There's a graph domain and there's a time domain, right? To make things simple here throughout this talk, we will only consider the graph domain, because somehow the time domain, we know how to handle that. So we will make abstraction of that today. So we will just assume that we have a single scalar measurement per node of the graph. But it's easy to extend that. So many researchers are currently looking at how to combine time domain with the graph domain, or even two graph domains, and so on. So you can have more dimensions, let's say. But here, to keep things simple, we assume a single scalar value per node. Okay, let's make things a little bit more concrete. So this is basically now the domain that we're talking about. So this will be the irregular support for our data, and it's characterized by means of a graph like this here. It has a set of nodes, V, and a set of edges, E, which are basically pairs of nodes. Right? And these edges can be many different things. They can be weighted, and that I try to indicate that here by the thickness of the edge. So let's say this edge here is thicker than that edge, so it will have a larger weight. We will also assume that the weights are positive, and they can also be directed, so like here. And these weights and the directivity is kind of indicated by what is called an adjacency matrix, right, which we call A, which has positive entries, and it's non-zero whenever we have an edge, and it's zero when we don't have an edge. Right? For instance here, this edge between 2 and n, it's undirected, so which means that actually we have an edge from 2 to n and from n to 2, and they have the same weight. So that's why these two entries in the adjacency matrix will be the same, and they will be non-zero. If we have an edge, a directed edge, let's say from 1 to 3, then we will only have one entry in the adjacency matrix that will be non-zero, and that will be the entry A31. And the entry A13 will be 0. Right? And that's how you can fill up this adjacency matrix, and that matrix will basically be another representation of the graph. So that's our support, and as I told you, this is what we assume to be given to us. Right? What these weights exactly represent depends a bit on the application. It can be, like I said, this represents data similarity, so the weight of the edge can represent how close how similar these two data points or these two nodes will be in the graph. Right, and on top of these nodes, we have then the signal. Right, and like I said, we consider just for simplicity a single scalar value per node. So we have on node 1 a negative x1, here a negative x3. So we indicate that by these vertical bars. Right, so positive x2 and negative xn. So every node has these signals present, and we simply stack them into a vector. So this is now not a vector in time or a vector in space. No, the index of these elements here, they indicate the node index. So there's no particular order. We can assume any order, but we should know the order, of course. So when I process this signal, I cannot do regular convolutions or regular Fourier transform, because that would not work. Because we should take the graph into account when we process this data. And I told you that, okay, this graph can be captured by the adjacency matrix, but that's only one way to capture the graph structure. Many other researchers, they use other representations. I will go into a few of those in a second. But in general, we can say that the graph is represented by what we will call a graph shift operator. It will become clear later on why we call it graph shift. But we indicate that matrix by S. And that S matrix is non-zero whenever we have an edge, but also on the diagonal we could have non-zero values, potentially. Right? And it can be the adjacency matrix, the A matrix that we defined before, but it can also be a so-called graph Laplacian. Right? And that is defined here. So Laplacian is actually the degree matrix minus the adjacency matrix. And the degree is nothing else than a diagonal. The degree matrix is a diagonal matrix, and the ith element can either be all the weights that come into that node, that is called the in-degree matrix, or all the weights that go out of that node, that is called the out-degree matrix. Right? So that's why in a Laplacian you actually have an in-Laplacian and an out-Laplacian. Now the Laplacian is usually used for undirected graphs. So in case we have a symmetric adjacency and hence also a symmetric Laplacian. So then it's just the in-degree and the out-degree are the same, and then the Laplacian is just the degree matrix minus the adjacency. Now why do some people prefer this Laplacian over just using the adjacency to characterize the graph? Well, because this Laplacian can define some notion of smoothness of a signal over a graph. If we look at this kind of quadratic form here, so X transpose, so remember X was the vector, was our signal. So if you look at X transpose Laplacian times X, this quadratic form, if you write this out using this definition here of degree matrix minus A, you can show that this is a superposition over all the edges, right, where you look at the differences of the two signals over every edge. And you square that difference, and you also weigh it with the edge weights. So you look basically at the differences over all the edges, the differences of the signal over all the edges. And if that's a small version, it means that the signal is kind of smooth over these edges. They don't change much over the edges. Whenever you don't have an edge, it can be a very big difference, but that difference is not considered in this summation, because for that edge, since there's no edge, so in that case this Aij will be 0. And if this quadratic form is large, it means we have big variations over the graph. So somehow people like this Laplacian because it introduces some kind of a smoothness notion. But like I said, so there's a group of people that prefer to use with the Laplacian, other people prefer the adjacency. Like I said, we will make abstraction of that, and we indicate both of them with S. And you pick your favorite one. There's even many modifications of those. You can normalize the adjacency, you can normalize the Laplacian, you can even translate them, you can shift them a little bit if you want. So there's many different variants, let's say. But we will work with this shift operator. Now why is this matrix important? Well, it turns out that this shift matrix, either adjacency or Laplacian, they introduce some kind of Fourier domain. If we take the eigenvalue decomposition of that shift matrix, and we assume for now that, let's say, the eigenvalue decomposition exists and that the eigenvectors form a unitary matrix, in that case we can write S, we can decompose S like this. So U is a unitary matrix, lambda is a diagonal matrix, and here this is just the complex conjugate transpose of U. And there are extensions for cases that the shift operator that the eigenvalue decomposition doesn't exist, or that we don't have, let's say, a unitary eigenvector matrix. But for simplicity, let's just assume that S is a normal matrix and we can decompose it like this. Then it turns out that for both the adjacency as well as the Laplacian, that these eigenvectors in U, they define some notion of frequencies. So if you look at, let's say, U1, it will be a low frequency, and if you look at U2, the frequency will be a little bit higher. But it's a frequency over the graph. So to give you an example, consider this simple graph here. I hope it's clear. So it's kind of a square between 1, 1, 2, 3, 4. It's a square, and then we have a connection between 4 and 5. If we look at the Laplacian, so this is the degree matrix minus the adjacency. Here we assume undirected, unweighted. And we take now the eigenvalue decomposition of this shift operator, which is now the Laplacian. Then here, in these vertical bars, we plot the different values of these eigenvectors. And we see that the U1 has all negative values, and they're all the same, so that's kind of a DC, right? A DC over the graph, you could say. And if we look at these other signals, they have more and more zero crossings over the edges. Right? When I say here 2 zero crossings, it means that over this edge we go from positive to negative, and also over this edge between 1 and 4 we go from negative to positive. So there's two edges where the sign of the signal changes. And that's some indication of variation in this case. That's how it's defined for the Laplacian. And you can see indeed that as you go up in index, which basically means that as the eigenvalues, the eigenvalues in this lambda matrix increase, decrease, we get higher and higher frequencies. Since we get more zero crossings. So in this case, for the Laplacian, the number of zero crossings defines some notion of frequency, of variation of the signal over the graph. What happens when you don't have an edge? We don't care about that. It's only when we have an edge that we want to see whether there's a lot of variation or not. And that holds true for all types of graph. You give me a graph, I can compute the Laplacian, then this will be true. That as you go up in the index, if you rank the eigenvalues from big to small, then you will see that we have more and more zero crossings. And that can be theoretically proven. So the Laplacian has some notion of frequency. Also the adjacency matrix itself has some notion of frequency. So if I would look at the eigenvalue decomposition of only this one, it will be different from the one for the Laplacian. So the eigenvectors are actually different because this is not a scaled identity matrix. But also for those, there is a notion of frequency. It's a little bit more complicated, so I'm not going to go into details there. It will not be related to zero crossings. But there's another notion of variability, let's say, that you can introduce. And actually the lambdas is what we will call the graph frequencies then. Right? So the u vectors will be the frequency vectors. So they will be related to the complex exponentials in the time domain. And then what we have on lambda is what we call the graph frequencies. So if we have an undirected graph, they will always be real. If we have a directed graph and the shift matrix is not symmetric, we can have complex graph frequencies. Now you could say, okay, how is this related to the time domain? Can I also view time domain now as a special case of a graph? And yes, you can. Right? If you consider this directed cycle here, where node 1 points to node 2, and node 2 points to node 3, and so on, and we look now as a shift operator, we look at the adjacency matrix, we get here a simple time delay, right? A circulant time delay. Right? So you see that we get like the identity matrix, but it's shifted over one diagonal. And we all know that if you take the eigenvalue decomposition of this matrix, that the eigenvectors will be the classical complex exponentials, will be the DFT matrix. So indeed, in this case, right, the graph frequencies, or the graph frequency vectors will be the classical DFT vectors. And what will be the eigenvalues in this case? They will be actually the complex values on the uniformly spread over the unit circle in the complex domain. So in graph signal processing, we view frequencies not as, let's say, 1 Hertz, 2 Hertz, and like that, but we view the frequencies really as complex numbers and as uniformly spread over the unit circle. So we view them as a to the e to the power j omega n. So those are graph frequencies. Those are the temporal frequencies for us. Right. So this basically this graph together with the adjacency matrix, they give us the, let's say, classical DFT grids, and they give us also the classical frequency grid that we have in time. But you can think of any other, let's say, circulant graph, directed or not, as long as the shift operator is circulant in some way, we know actually that the DFT matrix diagonalizes that matrix. So actually you could say that the DFT represents the graph frequencies for any circulant graph, directed or non-directed. Because in that case, either the adjacency or the Laplacian, both of them will be circulant matrices. Of course, in that case, the frequency grid will not be nicely uniformly spread over the unit circle, then we will get other graph frequencies. Right? So the frequency grid is not the same as in time domain when we have these type of graphs. That's only true for the directed cycle. But we can view time domain as a special case of this graph signal process. And so this U will then be what we call the graph Fourier transform. matrix. And so it generalizes the DFT matrix for signals that live on top of such a graph. And that means that I can do a graph Fourier transform, right? I can project now any signal on that graph. I can project it on these different eigenmodes, on these different graph frequency vectors, right? Which will be represented by this U Hermitian X. So X hat, this will represent now the different coefficients of these different eigenmodes. You can view these eigenmodes also mechanically, right? So suppose that your graph is really a mechanical graph and the edges are like springs with a certain strength that depends on the weight. When you start vibrating that physical graph, these eigenmodes, these graph frequency vectors will be the vibrating modes of that mechanical graph actually. So there is, let's say, kind of a physical interpretation as well. And so you can do also the inverse transformation. And so once we have a graph Fourier transform, we can also think of filters now, right? Because we can now magnify certain graph frequencies or attenuate specific frequencies. So that just means that in the graph frequency domain, so we have, for instance, the nth graph frequency, we can multiply it with this kind of function, h of lambda n. So lambda n will be the nth graph frequency. So this one can be smaller than 1, so when we want to suppress, or bigger than 1 when we want to magnify it. And that is the output of our filter, or the nth frequency mode. So in the frequency domain, it looks like an element-wise product. So we have here a diagonal matrix. With on the diagonal, we have actually our frequency response of the graph filter in that case. And here we have the input in the frequency domain. So in the graph frequency domain, it's like a time domain. We just have an element-wise product of the signal with the filter. And what does it mean now in the graph domain? Well, we get kind of this relationship here. So, yeah, sorry, if we go back to the vertex domain, the node domain now, how does that operation look like? Well, so this, remember the U Hermitian X with the X hat, so then we have the diagonal matrix, and with U we go back to the node domain. So we get kind of this linear operator here as the filter operation in the node domain, which is nothing else than just a matrix, right? H. So graph filtering is nothing else than just a linear matrix vector multiplication, H times X. But this H has a special form. It is diagonalizable by this U matrix, which is the graph Fourier transform. Compare this to the time domain, where H would be a circular matrix in case we look at periodic time, because I said that time is a special case of a graph. Actually, it's periodic time is a special case of a graph. And filters in periodic time would be represented by a circular matrix, right? And indeed, if H is a circular matrix, then it can always be diagonalized by the DFT. Here, if I give you an H, it's harder to see whether it's really a graph filter operation or not, because it has to be diagonalized now, not by the DFT, but by some matrix U that depends on the graph itself. But this is, let's say, an eligible graph filter. So any operator H that is diagonalizable by the graph Fourier transform. So it cannot be any linear operator. Now, why is this useful, right? So you can say, okay, fine, do I need all this? I could as well immediately say that we just do linear transforms of graph signals and that's it. Well, I mean, this interpretation as a filter and as basically a convolution has interesting applications. One of them is, for instance, denoising signals. So suppose that we have this kind of social network where with different communities, and so within communities we have lots of connections, and over communities we have less connections. Although you see many edges here, there's much more connections within the communities than over the communities. Now, suppose that I have a certain opinion about a certain political party, for instance, right? So here we have the socialists and the liberals and the green, some green communities. But suppose that these opinions are a bit noisy, right? So we want to do denoising. Then we want to denoise in such a way that we only remove outliers or noise values within the communities, not over the communities. And that's exactly what a graph filter will do. It will smoothen things only over edges, not smoothen things between values that are not connected by an edge. And that's what you see after denoising, that you don't get any leakage from the red and the blue because they are different communities. So I don't want to smoothen over those different communities. I only want to smoothen within. And that's implicitly done by such a graph filter. Another application is interpolation. Suppose that some nodes don't have a value of the signal. So in that case, I want to interpolate this somehow. And we can do this again by running a kind of a low-pass graph filter over that graph signal. So suppose that this red node is not available, it's corrupted, it's a corrupted sensor node, for instance, then I can basically run a graph filter and then that will give me the value for this red node. Which basically means that I look at my neighborhood and I try to take some kind of average of my neighborhood. That would be, let's say, a simple way to do that. But the graph filter does it in a more clever fashion. Also to analyze, let's say, certain diffusion effects. Think again of this traffic network. Suppose that there's an accident somewhere and you want to see how this spreads, how the number of cars that cross a certain junction, how that affects, because all of a sudden there's an accident, so the signal will go to zero. So how that diffuses over the graph can also be kind of modeled by such a graph filter. So to analyze certain diffusion effects, we can also use graph filters. And then very recently, these graph filters are also used in deep learning now, more particularly in convolutional nets. So you know that these nets are used for all kinds of classification purposes, but again, only for regular data structures like audio or images or video. And then in between layers, you can run a regular convolution, a regular filter basically, or a bunch of filters, right? Many filters. But what if you have data that has this irregular structure, right? So data that lives on a graph, then I cannot run just a regular filter on that because it would not make any sense. So then we have to take that graph into account and apply a graph filter in between the layers, because that is now the right definition of a convolution in that domain. So and you see now many papers appearing very recently where indeed in between layers they're going to use these type of graph filters, and you can learn them the same way as you do it in classical convolutional nets. So that's now a very hot topic where this graph signal processing is being used. And okay, this can again be data from social networks that you want to classify, or people also use this to attribute authorship of certain papers to see if that's indeed the correct author for a paper. Because okay, how do you run a convolution on a paper, right? So somehow you can transform that paper maybe in a signal, but so how do you do that? And since language can be represented by a graph, the best way to do a convolution on an article or on a paper is by using a graph convolution on the so-called word adjacency network related to a certain language, for instance. So these things are being developed right now. So it has many applications, let's say, these graph filters. Right, so, okay, so now how do we design these filters and how do we implement them? Right? First, the design, I'm going to be quick about that. So this is kind of a general overview. Later on, we go in a little bit more depth. Let me just say about the design that there's a graph-dependent design and a graph-independent design. So the standard way to design it is assuming you know all the graph frequencies. So you've taken an eigenvalue decomposition of your shift operator, you know the graph frequencies. Let's say, suppose you have 6 of those, and then for instance you want to do like a low pass characteristic here, so lambda 1, lambda 2, lambda 3 you want to keep, and the rest you want to put 0. And then you get this kind of graph design. And there are ways to do this in an exact fashion. So this you can achieve exactly. But more interestingly is to do the filter design actually independent of the graph. So you want to design filter coefficients. We will later on see what exactly we mean by filter coefficients. But we want to design these filters such that they have a low pass characteristic for any possible graph. Right? Is this possible? Well, yes. Because there are cases where the shift operator has a limited possible set of lambdas, or a range of lambda of graph frequencies. For instance, a normalized Laplacian, we know that the lambdas can only be between 0 and 2. So what we do in this graph independent or so-called universal design is we try to find a filter design that has this low pass characteristic over this continuous range of all possible lambdas. You can think of this as kind of a continuous frequency domain instead of a discrete frequency domain. So we designed the filter over the continuous graph frequency domain, the whole range, and that we cannot do exact, so we will not be able to perfectly get a rectangular shape, but we get kind of the blue shape. But even with the blue shape, so now whatever the graph is and the graph frequencies are, I know that the graph frequencies will be distributed here somewhere. Then still I will know that, okay, the lower ones, they will be kept, and the higher ones, they will be removed. So any graph you give me with those fixed filter coefficients, the filter will always implement some kind of averaging, some kind of low pass characteristic. I mean, a simple example is just if you say the filter design is such that we average the neighbors. So if that's the filter coefficient tells you that you just talk to your neighbors and you average those values, that will always be a low pass characteristic, right? So whatever the graph will be, if that's how you design your filter, then it will always implement a low pass characteristic on your graph. And that's basically what we do in this so-called universal design. But I'll show you some examples later on. So what about the implementation? So we know for temporal filters that we like to implement them often in the frequency domain, right? Because we can go quickly to the frequency domain by means of the fast Fourier transform. And then in the frequency domain, we just have an element-wise product, right? So that's very efficient. But here we cannot do that because so far people have not yet developed fast transforms, fast graph Fourier transforms. At least not for general graphs. There are some particular graphs where you can implement it in a fast way, but for a general graph, there's no fast graph Fourier transform. So basically this means that you have to do a full matrix vector product here to go to the frequency domain. And on top of that, you have to know, first of all, what the new matrix is. It depends on the graph. So I first have to do a full-blown eigenvalue decomposition to know what is the graph Fourier transform, which could be very complex if you have many nodes. So actually in this graph domain, the filter implementation is usually done on the nodes themselves. So we don't go to the frequency domain. We just try to implement this kind of matrix vector product, h times x. But even that one could be very complicated. If you have thousands and thousands of nodes, then still this matrix vector product, might be a very complicated task. And that's why the whole field of filter design is actually looking at some kind of parametrized versions of this H matrix. So can we parameterize it such that it still satisfies this kind of diagonalizability by the U matrix, by the graph Fourier transform? But we want to parameterize it such that this H times X is simple to implement and maybe even implementable in a distributed fashion. And that's what we will see now. We will see many of these parameterizations for H that satisfy this property. They are diagonalizable by the graph Fourier transform, but you can implement this in a simple fashion. And one of the popular and the first developed graph filters was actually, or parameterizations, was actually this one, where you write your H operator as a polynomial in the shift. Right? And you can easily show that this form is diagonalizable by the graph Fourier transform, because S is diagonalizable by the graph Fourier transform, and then it's easy to show that the powers of S are as well, and so the whole matrix here is an eligible graph filter. And the frequency response is nothing else than this kind of polynomial in the graph frequencies. So, and indeed now, if you replace S by the classical delay that we had, which was our time shift, and we replace the lambdas here by the e to the power j omega n, then you get your classical FIR filter and its frequency response. Right? So indeed, this is an extension of FIR filters, but to this graph domain. That's why it's called FIR graph filters. And I forgot to mention, that's also why this S is called the graph shift, because now it plays kind of the role of what the delay plays in the temporal domain. Right? Remember, in the time domain, S is nothing else than a circulant delay. But here it's more general, right? It kind of diffuses your signal. Doing S times X is kind of doing a diffusion step. Now, is this easier to implement than just doing H times X? Well, yes it is, because now we have to multiply S with X many different times. But S times X can be implemented in a very efficient manner because S is a very sparse matrix. It has the same sparsity pattern as the graph itself. And doing higher powers of S, so S to the kx is nothing else than applying S to the power k minus 1x, which means that I have to multiply x with S, capital K times. And if k is low, then that's a very efficient operator. And more efficient than multiplying h with x, because h could be, yeah, like I said, 1,000 by 1,000 or whatever. And multiplying S with a vector can also be easily distributed because it just means that I talk to my neighbors and I combine the information using the weights in the S matrix. Because S has the same sparsity pattern as the graph, like I said. So S times X is very efficient, centralized, but it can also be very easily distributed. So even that whole filter operation, H times X, can be very easily distributed. There's also no stability issue. The only thing is that if you give me a desired response, I have to fit a polynomial to it. Right? Because I know that my impulse response, my frequency response of my FIR filter is this kind of polynomial in the graph frequencies. Right? And we know that polynomial fitting, it's not a well-defined, or it's not a very stable problem, let's say. It's often ill-conditioned, especially if the order is very high. That's why in FIR filters, we usually try to keep the order kind of low. Here you see the design. So how do we design this? Like I said, it's just polynomial fitting. So you pick your favorite polynomial fitting algorithm. Right? So I give you a desired response, h hat sub n, so for the n frequency component, and then I have to fit a polynomial to it. So the simplest way might be just to do a least squares fit, because this error is linear in the phi's. So I can just solve the least squares problem and to find my phi's back. But here the system matrix, this psi is a matrix of the eigenvalues, so this will be a van der Monde matrix. And we know that that's not always a very well-defined or well-conditioned matrix, so especially if you get many columns there. Now, how do we distinguish here this graph-dependent and independent design? So I told you there's two cases. Well, you can apply both to this least squares problem. If you know the graph frequencies, okay, that's fine. Then you just plug them into psi. If we don't know the graph frequencies and we want a design that holds for all possible graphs, and we somehow know the continuous range in which all these graph frequencies are located, then we just do a gridding of that range, and we assume we put all these lambdas from that grid into the psi matrix. So you either put the true ones there or you put a grid of lambdas there if you don't know what is the graph. Another graph-independent design that has been also very popular is this kind of Chebyshev design. So in that case, you're going to express your desired response in the continuous range of graph frequencies as a series of Chebyshev polynomials, and we know that this can be exactly expressed like that. And the C coefficients, they are well known, they can be computed in closed form, and then we're just going to cut this off up to order k. So here also, this one is also nothing else than actually a polynomial of order k, like this expression there. But now I don't have to solve the least squares problem. These C coefficients are given somehow in closed form. And we know that cutting off such a Chebyshev series always gives you a good fit. Right? So this is also a design that holds independent of the graph, because you don't have to know the actual lambdas. You just design this fit for a whole continuous range of lambdas. There have been many extensions then of these FIR filters. Basically, these are some extensions that in time domain would be the extensions of a time invariant filter to time varying filters. Right? Here, you can call it a node varying filter or an edge varying filter. So you just replace this phi by either a diagonal matrix or a full matrix with the same support as the graph. But I'm not going to go into details, but you can imagine that these two can fit better a certain operator H than this one. The problem is that they are not eligible graph filters anymore, so they're not diagonalizable by the graph Fourier transform anymore. So actually they're more like a time varying convolution, or the extension of that to the graph, you would say. There's also all kinds of nonlinear versions where people are looking at. median graph filters, or putting an activation function after the outputs, right, which is what you will use in a graph convolutional net, of course. You could also think of Volterra graph filters. People have not yet looked into that, but that's also possible. We actually started in this field of graph signal processing by looking at infinite impulse response filters, or so-called autoregressive moving average graph filters, because everybody was for a long time looking at only at these FIR filters. But you can also do the IIR version, and in that case, the H is not a polynomial in S, but it's basically a rational polynomial in the shift operator. So we multiply the whole thing also with this inverse matrix here, which is an inverse of a polynomial in the shift. And this one is also diagonalizable by the graph Fourier transform, and now the frequency response is nothing else than a rational polynomial in the graph frequency, so instead of a polynomial. And this is an advantage, so you can do a much better fit of certain desired filter shapes, which we know from time domain as well. Actually, the interesting thing here is that we don't actually have stability issues. You might remember from your classes that for an IIR filter to be stable, you need your poles to be inside the unit circle. Well, there's actually no such thing here, because actually the graph is always finite, so nothing ever blows up to infinity. It's the same as periodic time, right? In periodic time, you actually also have no stability issues. It's only when you have infinite time that you have stability issues. So you only have to make sure that actually this denominator here is not zero. That's the only thing you have to make sure. The interesting thing is that also many inference problems, if you write them down, and if you write down the closed form solution for those, like Wiener denoising or something like that, they often have the form of an IIR filter. Right? So it's better than to also consider them as an IIR filter and to implement them as such than to approximate them by an FIR filter, which is what was done before always. The only problem is that, okay, the design might be a little bit more complicated and also the implementation. But okay, so in view of time, I'm gonna skip how you do those. But it is also possible to implement those in an efficient manner and to design those in an efficient manner. Actually, to design again, you use your favorite rational polynomial fitting algorithm, which could be Prony-like or iterative approaches and so on. And for this inverse, to compute this inverse, you can use all kinds of clever inversion methods. So let me just show some design simulations. So here you see, so this was for an ideal low-pass filter with a cutoff of 1, and we want to see how close our design is to the true low-pass filter with cutoff. And we compare the FIR with the IIR, so this is the order of the FIR, and whenever we look at the IIR, we make sure that the order of the numerator and denominator, the sum of the two is never larger than the order of the FIR filter. And you see in green it's the FIR filter, so you see that even at high order, it kind of saturates because you get also this Gibbs phenomenon there. So you can actually never improve the mean square of the fit because of also the ill conditioning of the system matrix in the least squares problem. But with the IIR filter, you can get better designs. So this is a Prony design, and this is sort of iterative design. And the numbers that you see in the curve is actually the optimal value of Q in that case. But there we see as the order increases that we get better and better fits for the IIR filter. Implementation, like I said, I'm going to skip that also. But you can implement it in an efficient and a distributed fashion. Now let's move on to the spectrum to statistical graph signals. Right. So far, I assumed that the signal X is kind of a deterministic signal. Right? Suppose this is now a random signal. It has a mean and a covariance matrix. Let's assume not Gaussian, and let's assume Gaussian and just focus on second order statistics. Even if it's non-Gaussian, let's just focus on second order statistics. And then the question could be, okay, well, can we now define also something like stationarity of that random signal over the graph? Wide sense stationarity, since we focus on second order statistics. And that's kind of a difficult question, right? Because we know from time domain, we can easily define stationarity there. We know that the mean and the correlation function doesn't change over time. It only changes with correlation lags, right? But okay, what does that mean here, like correlation lag, for instance, right? Because we have this very irregular structure characterized by a graph. The graph can be dense in some area, very sparse in some area. So how can we say that the statistics of a signal do not change over a graph if that graph is very irregular? So how can we define that? And so people, a few years ago, so people have been looking into that and came up with many different definitions. It turned out later that many definitions kind of overlap. And since we were talking about graph filters here, maybe the best definition is given by a graph filter. Basically what this definition says is that you can obtain a stationary graph signal by filtering white noise. The same as in time domain. The only difference here is that the filter is this graph filter that is actually diagonalizable by the graph Fourier transform. We also call it linear shift invariant filter because I didn't yet mention, but the fact that this H matrix can be diagonalized by U also means that it can commute with the shift operator itself. So first shifting and then filtering, or first filtering and then shifting is kind of the same. So applying a graph filter to white noise gives us such a wide sense stationary graph signal. So that's the right way, let's say, to say that the statistics of this filtered white noise are not changing over the graph. Because it's the graph filter itself that takes into account that the graph is dense in some areas and sparse in other areas. But there are other definitions which are related. And so, by the way, I assumed here for simplicity that we just have a zero mean. There's also a discussion that you can have related to the mean, but for simplicity, let's assume zero mean here. Now, okay, what is the covariance matrix now of this X? Well, it's nothing else than, since this has covariance matrix identity, it will be H times H Hermitian, and since H is diagonalizable by the graph Fourier transform, Rx itself, so the covariance matrix, can also be diagonalized by the graph Fourier transform. And what is on the diagonal? Well, that's our power spectral density. And so again, compare it to time. In time domain, H was circulant, so H times H Hermitian is also circulant, so Rx is circulant, so you can diagonalize there also the covariance matrix by the DFT, and on the diagonal you find the temporal power spectral density. Here, the same thing. So this is now the power spectral density of that signal on the graph. And it's useful to estimate this based on data, because then we can do all kinds of statistical inference now. Before we were just doing Wiener filtering, you could say we did like deterministic inference, but if you want to do statistical inference, then we need this power spectral density, and that's the right way to define it. Right, to give you an example, this is actually adjacency matrix of some karate club social network that has been used in the community in a number of papers. And suppose that we consider now a random signal on top of this graph, let's say an opinion process, right? And this is the covariance matrix. Right? If I ask you now, is this the covariance matrix of a stationary signal on top of this graph? It's very hard to see that. If it would be time domain, it's very easy to check from the covariance matrix whether you have stationarity or not, because you need all the diagonals should be the same in case you have stationarity in time domain. Because we know that in time domain the statistics do not change. But here it's perfectly possible that this is that this one is stationary on this graph. The only thing we have to do is we have to check whether these two matrices are jointly diagonalizable. So if I diagonalize this one and I get the graph Fourier transform and I apply it to this one, what do I get? I get the diagonal matrix. So indeed, right, both are jointly diagonalizable. So we can have now very unstructured covariance matrices, but they still can be considered stationary over a graph. Actually, any process you give me, I can always figure out a graph over which that signal is stationary. Because I can just build a graph. I can just replace this shift operator by the Rx itself. I say my Rx, my covariance matrix, is my shift operator. And then I have a graph on which that process is stationary. But like I said in the beginning, the graph is usually in graph signal processing given from another domain, right? So I cannot design my S. I assume it's given, and then I'm going to check whether some process is stationary on that graph. And now estimating, so estimating that PSD, right, is, like I said, important for all kinds of statistical inferences, and that is nothing else than the extension of spectral estimation, but now to the graph domain. And you can think of nonparametric and parametric forms of that. So the nonparametric is the same as in time domain, so we can look at the periodogram and the parallelogram. So assume that we have a number of realizations, x1 up to xns, so we can just translate every one of those to the Fourier domain, look at the power on every carrier, and that's my power, an estimate of my power spectral density, right? That's the classical periodogram that you probably all know very well, or the correlagram. So you take an estimate of the covariance matrix in the node domain, you project it onto the graph Fourier transform, and you pick the diagonal entries. And we know that these are the same. They are the same in time domain, and not surprisingly, they're also the same in the graph domain. And even you can check the properties of this estimator. It will be unbiased, and the variance, as in time domain, is again given by the square of the power spectral density itself. This is if you have a number of realizations. If you only have given one realization, you have to use these kind of windowing methods or filter bank methods, which have also been proposed, of course, in time domain. So also those you can extend now. I'm not going to go into details, but let's say the Welch method, you can apply it, and all these filter bank methods you can also apply. But not everything is easy to extend. For instance, in the windowing methods, you could now wonder, okay, what type of windows should we use here? Right? In time, it's obvious, we just use consecutive samples, temporal samples, and those are our windows. Here, yeah, what should we use as windows? Should we do first some kind of clustering and use those as windows, or should we just randomly pick nodes and say, okay, this is one realization, and then I randomly pick another set of nodes, and that's one realization. So there's still work to be done in that respect on optimizing these windows, for instance. What about the parametric methods? Well, in the parametric methods, we're going to view these processes as coming out of a parametric filter applied on the white noise. Right? So we've seen FIR filters and IIR filters. So now we can, for instance, look at the moving average graph process, which means that this is nothing else than the process that is obtained by filtering white noise with an FIR, or so-called moving average filter. So this is the filter, the H of H that we saw before. Right? So now the coefficients are not phi, but they're H. Right? So this is nothing else than an FIR filter, and you filter white noise. Now, of course, the covariance matrix is not nicely linear anymore. It's kind of a non-linear, right? It has a non-linear shape. We have the same problem actually in time domain. But you could do some kind of non-linear least squares now to find these filter coefficients. But there is a case where we can linearize it. Actually, for undirected graphs, you can actually show that instead of this kind of complicated nonlinear function of the filter coefficient, we can write it as a linear form where the b's are kind of the squares of these filter coefficients, or all kinds of correlations of filter coefficients. So it is possible to linearly parameterize that. Of course, the coefficients are not directly the h's here, but we can derive from the b's, we can derive the h's. But then we can do just a linear least square, so that solves that problem. So it is possible to in some cases, to linearize that. The same for an autoregressive graph process. So in that case, our filter is this kind of inverse polynomial, right, with A coefficients. Again, the covariance matrix is H Hermitian, but now H is nonlinearly related to A. So again, we can do nonlinear least squares if we want. And what is the right way now to linearize? That is to use some kind of Yule-Walker ID. So this is the extension, let's say, of Yule-Walker to the graph domain. So you write your process. So actually, if you look at this here, so I can bring, if I bring this to the other side, I get identity plus a polynomial times x is equal to n, and that's the same as this, right? So x is a FIR filtered version of x plus n. So if I multiply both sides with x Hermitian and then take the expected value, then I get this thing here. So I can express my Rx as a linear combination of my filter coefficients A. note that the Rx is also here, right? But we can estimate Rx. So we can estimate Rx, plug it in, and then solve that with a linear least squares problem. So both the moving average as well as the autoregressive, it is possible to find the unknown parameters using linear least squares. And of course, these parametric methods have the advantage that I have to estimate less parameters than the non-parametric method. Some simulation results. Again, on this Karate Club social network, where we assume a process with this PSD, the blue line. And so these are different periodograms for different realizations. Of course, the more realizations, the closer we get to the truth. This is for a single realization with one window, which is of course very bad, or 4 windows, which gets a little bit closer, but the windowing also only really works well if you consider a little bit more realizations. If I do the parametric, for instance, the moving average, then even with one realization, we get a very good fit because we have to estimate less parameters. Right, so I think this brings us to the conclusion. So I started with an introduction of what are graph signals and why is it useful. Then we looked into this graph filtering because we introduced the graph Fourier domain, so that leads to filtering. And then we can use for denoising, interpolation, and now also very popular these graph convolutional nets. We looked at FIR filters as well as IR filters. Actually, both are currently used in these graph neural nets, although they don't always cite the graph signal processing literature, but they are basically either FIR or IR filters. We then used these graph filters also to define stationarity and to do power spectral density estimation. And for future work, we're also looking at graph sampling. So I didn't talk about this today, but also the whole sampling theory that we know from time and space can be extended to the graph domain. Which node do we have to sample to reconstruct the band-limited graph signal? Because we have defined the graph Fourier transform, so we can define band-limitedness of signals on that graph. We've seen actually also smoothness, right? The quadratic form in the Laplacian. That's a definition not of band-limitedness, but smoothness, but they're close. So how do we do sampling for reconstructing these smooth or band-limited signals? Or even graph sampling also for estimating the power spectral density. That's also possible. We're also looking at these edge-varying graph filters, so these kind of extension of time-varying filters to the graph domain for distributed optimization, because it turns out that there are close relationships between the two. We also want to look at local stationarity, maybe cyclostationarity, and very recently we also jumped into this field of graph convolutional nets, and we try to look at all kinds of different architectures and try to get some intuition behind the working of those. With that, I would like to thank you for your attention. Any questions? Comments? Yes.
Well, thank you very much for your talk. It seems that you need the graph a priori. So the question is, how sensitive is the whole methodology on small differences on the graph, and whether have you seen any joint techniques to both extract interesting features of the signal as well as build the graph? Using the data that you collect from your sensors or from the drones.
Yeah, that's a good question. So to answer the first question, so the first question was, remind me again.
Sensitivity.
Yeah. So how important is to have the exact knowledge of the graph? Well, I think if you think of these brain networks, for instance, right? So and you look at fMRI images, so you can process these things spatially, right? And so that is a rectangular grid, and like I mentioned, this is actually not the right graph, but still it kind of works, right? But you will get better results if you use the true graph. If that is not really the ground truth, or maybe you miss some connections, that will not have a very big effect, but it will have an effect, right? But if you then design, again, you have a certain property, so you want to design also your filter coefficients given that graph, so that that design can also help to create some robustness, because there you use that exact knowledge of that graph. But it's indeed, that is the prior knowledge that you have in this field that you don't have in classical signal processing, and it might give you an advantage. Indeed, I'm not claiming here that if you take the completely wrong graph, you will do worse than just processing it spatially, actually. And yeah, so about estimating the graph itself and maybe filter coefficients together with the graph. So indeed, so there are works where they do both jointly. For instance, you have an autoregressive kind of process in time even, and you want to not only find the autoregressive coefficients, like what I discussed here, but also how they are connected. Right? So it's of course a more complicated, highly nonlinear problem, but there are works on that. And there's even more works on where you don't care about the filter, but just want to get some kind of graph topology from data, right? So that's like topology identification, and that's probably an even older field than graph signal processing. Now people within graph signal processing are also looking at topology identification, and they try to use these ideas of stationarity and things like that to find the topology of the graph. And those techniques, they can outperform what was done before. Of course, it's not always clear. In some applications, there is no ground truth graph, so it depends a bit on what you want to do. Other questions? Yes.
I have a question regarding your first part of your talk, which unfortunately I missed now. So I just, by imagining what you have said, I just want to make a question. If we look at this graph shift operator you have, it acts on a space of signals, namely a finite dimensional Hilbert space. It has some certain dimension. In some of the cases, it would be nice to have periodic boundary conditions, even from the premises of the problem of you can put them by hand and remove it later on by going to a large limit or whatever. Now the thing is that it is possible if you have some complex Hilbert space of dimension n, and if this n without loss of generality is a composite number, you can always decompose into products if you pick up a kind of co-prime divisions. Mm-hmm. So for example, if you have a hexagon, for example, you can decompose the Hilbert space, which is sixplet of complex numbers, into pairs and triplets of numbers. Okay. So the Hilbert space decomposes in a kind of bijective way, one-to-one. So your shift operator will also decompose in this tensor product of Hilbert spaces. And the whole machinery you have with operators and so on will also decompose. Mm-hmm. That is to say, if your problem is not so bad, it's linear and so on, we can decompose the graph you have, the hexagon graph, to a graph with 2 points plus a triangle. You can solve the problem by distributing in these two ways the parts and then put it back. Mm-hmm. Now you have obviously some advantages because of the smaller dimension and so on. Right. And this is all will be based on the composite number decomposition. So you need something like a Chinese remainder theorem to tell you, for example, that 6 decomposed to 2 prime 3 and so on.
So there might be indeed applications where these structured graphs appear, right? So
yeah. So my question is that have you tried something like that?
Yeah. So actually, because I started with saying that we can go here. I started with saying that for now we just assume that we have a single scalar value per node, right? But you could have a whole time series per node or a whole vector, right? That by itself might also have a graph structure. If this, instead of a single scalar value x2 here, is a vector x2, which represents maybe the time vector, we know that that is a line graph. So then we have kind of a product of this graph here, very irregular, with a line graph. And then you can do joint time processing, graph processing on this kind of product graph. There's different variants of the product graph. But so in that context, people have done that. Or even, like I said, even x2 can be a vector with another graph. So you have a graph of the features on top of the nodes, and you have the graph as the domain. So you have two graphs, and you consider a product graph. And indeed, all the filtering, all the operations kind of decompose over these two graphs, and then later you can combine it again. So people have been looking at that. We in particular, for the case where x2 is not a scalar but a time series, which can also be represented by a very structured graph. But there might be, maybe, I'm not sure what type of applications you have in mind, but there might be indeed other cases where you have highly structured graphs.
Well, in fact, it's very interesting that you can decompose your original problem in some irreducible components based on this decomposition of the number theory. And you can have completely different components of the initial problem, which you can dissolve and then put it back, solve the separate problems. And this decomposition is exactly unique because the decomposition of the number n is also unique. It stems from this fact, it's completely, and you can go back and forth actually. And in fact, you can even, if you want to do some kind of very fine structural resolution into the most simple residues when you divide, or you can do some kind of coarse graining kind of decomposition. Namely, you can decompose n to n1 times n2, n3. And n2 can be also a kind of number that still can be decomposed into reducible components.
Okay, that's interesting. Thank you. Yes?
I must confess that I was not familiar with the topic and I'm impressed by the talk. I will make one question which might probably see. I knew nothing about the specific applications, the graphs, all these things, and how you see graphs. But I knew most of the things and techniques that presented in order to solve the problem. My question is, perhaps, for example, locus filtering, we can define somehow what is meant by locus filtering in the graph and do this somehow without using the graph. Perhaps you say that a lot of locus filter is averaging over the neighbors, for example, can find more and more there are notions. My question, I suspect this might be the answer, but I would like to hear the answer by an expert in the field, is that with all this bunch of techniques, you solve new problems that cannot be solved otherwise, or you offer alternative solutions to problems that can somehow be solved otherwise, or you are presenting a toolbox of techniques that have, let's say, more or less general applicability on many problems that, in order to solve each one of them, you must solve a different problem and so on. So what's your view about this field, which is new to me?
Yeah, so I agree with you that indeed some of these filters that I presented, they're not new, so they have been developed. So like, okay, averaging the values of your neighbors, that gives you also good interpolation and some kind of low pass on the graph. That is of course obvious, and that already existed, of course, before graph signal processing. But this puts all this kind of in a new viewpoint, in a new framework, and allows you to actually couple this with everything that has been done in classical signal processing. So it generalizes the domain, and that allows you then also to look at other types of interpolation which have not yet been developed. So because you give it kind of you bring it into this kind of unified view, it gives you also new types of solutions then to existing problems that were already solved, but now we can do it better by taking tools from classical signal processing into account and generalizing them to the graph domain, basically. So I see this more as kind of a unified view, and indeed many different fields came to this graph signal processing from different applications, from image processing and also more theoretically even algebraic signal processing. So there were people that tried to define what is signal processing axiomatically, and they also came then to this kind of generalization of graph signal processing. So so it doesn't, let's say, it gives a nice interpretation to already existing tools, but it also allows you then to make better tools. Yeah, so I think that the field in the beginning was a bit struggling with that. People were extending many of the concepts that I also explained today. But I think now, especially with the brain networks, so there you see some new developments where people use this spectral information of fMRI signals on the brain graph to infer certain diseases or attention span, and so basically cognitive properties that you can actually infer from the spectral content of a signal over the brain graph. So there you see some interesting developments, and then also the use in graph neural nets, that's also really taking off right now. So I think that's also where these graph filters are going to be very useful.
Any other question?
Yes.
Yes. Thank you for the presentation. You mentioned that there is a way to take a non-stationary covariance matrix and find another network which has stationary covariance matrix. Can you give us some hints on how this can be done, or maybe literature on this?
Yeah, it's very simple actually, but so here this was the shift and this was the covariance, and I said okay, they're jointly diagonalizable, so that's why I can view this one as being stationary in this. Now suppose instead of this one here, I just use the same matrix. I say my shift operator is equal to my covariance. So the weights of the edges are just covariance values. So I have a fully connected graph, and the weights of my edges are just in here, or just the covariance values. And of course, they are just the same matrices now, so of course they're jointly diagonalizable. And so, but it doesn't, in that case you don't really gain anything, right? Because you use your covariance matrix, which you already had, to now design a graph. So, okay, you can say now, fine, so I can use statistical signal processing and linear filtering because I know it's stationary, but this will be the regular processing that you would have done otherwise anyway. So there's no new information that somebody has given you, from another field. They have not given you like a brain graph or a road network, which you know is somehow related to that data. So that's why, it would not make sense to replace this social network with this covariance. And of course I gave you now kind of a toy example. In practice, if I would look indeed at this data of number of cars crossing a junction and the road network, and I would check whether it's stationary on that graph, it will never be perfectly stationary. Right? It will never be perfectly diagonalizable. But we know that in reality, in the time domain, there's also no actual stationary signals in practice, right? The speech signals, for instance, they're not stationary. Still, we use lots of tools from statistical signal processing, which are based on stationary signals, and they still work on these or approximately stationary signals. That's why, even if this is not perfectly diagonalizable, but we have a very high diagonal component, it's still useful to estimate the power spectrum and do all kinds of statistical inference methods.
Any other question?
Can I ask one more, please?
Yes, but shorter.
Very short. Do you see any application in this so-called expanded graph, where you have a graph where the size of the boundary is the same like the total number of the nodes, which are mostly applied in the case of social graphs?
Okay. I don't see directly, I don't see directly an application. Maybe you know better than
No, this is a question, because for example, in an ordinary graph and in an expanded graph, you have a different diffusion laws, actually, because of that. So I thought how this shows up in the case of signal processing in expanded.
That I don't. So people have been looking a lot at bitype graphs and things like that, which even in image processing they are useful. And wavelets. So people have also, I didn't mention that, but there's a whole theory on wavelets over graphs, which were used for doing image processing. But then you build the graph based on the image also, and then you apply wavelets for that.